Hello, welcome to my virtual talk on application of interface guided waves for structural health monitoring of hybrid bonded joints. My name is Mark Jahanbin, and in the next few minutes I will be introducing a novel inspection method for non-destructive inspection of hybrid bonded joints. Here is the outline of my talk. I'll be talking about high-frequency ultrasonic interface waves and the way they can be used to reveal structural damages for some aerospace application. First section, I get into the objective and the premise of my research and describe the problem statement. Then I will demonstrate 5 applications and the structural defect scenarios for this work. The premise of my research study is to develop a novel inspection technique for bonded joints. There are basically 2 primary ways of joining parts together. We can either bond them with some sort of adhesive, or we use fasteners like bolt and rivets to put them together. In today's aerospace structures, where the application of composite are increased significantly, the bolted joints with traditional fastener is no longer a preferred method for composite attachment, because first drilling hole into composite is not easy, and there is a complex technique such as orbital drilling to create a notch or hole into a structure. And second, composite are notch sensitive, and by drilling we break the fibrous structure, and in fact we introduce damage into them. So the preferred method is adhesive agent by some sort of method like co-cure and co-bonded. Problem is that presently we don't have any established method in industry, to measure the strength of the bond. So regulatory agencies, they have some requirements. I have listed a couple of them here. So they propose that we should have an analysis method for the bonded joints, which is my job role as a structural analyst and what I do for a living, or test the bond section, which involve heavily on proof testing of each component. And the last part, which is the interest of my work, is develop a reliable and repeatable inspection method for non-destructively measure the strength of the bond. Hybrid structures are mechanical joints which are made of 2 or more material with different mechanical properties. In design, when we target the optimized material used, the best option is hybrid joints. Since my background is aerospace, I have a few examples from aircraft parts. So in the middle you can see wing box structure, where we have a composite panel and a spar attached to the aluminum or titanium fixed trailing edge here in this case. Or this floor beam, we have a composite web attached to the titanium flange, and also these hat stringers. They are all hybrid structures. It's not just manufacturing and repair. When we try to establish a structural integrity to the damage section, we do a scarfing using metallic patchwork composite or different composite with lower cure temperature. Also additive manufacturing. In additive manufacturing, layer by layer deposition of material create a hybrid structure. Since we are talking about reliability and repeatability of the inspection method, it's imperative that we look at all the inspection methods for both metallic and composite structure. Considering today's technology, associated cost, and accessibility to the tooling, ultrasonic is the best known method inspection that works well for both isotropic and anisotropic material like composite. There are 2 major classifications in terms of high frequency ultrasonic wave propagation: bulk wave, guided wave. Bulk wave are acoustic elastic wave propagating in the media like solid, and guided wave are, which is a primary focus of my research, those are the type of the waves that are propagate by the boundaries of the media. But either way, when the wave propagates into a structure, any defect and damage cause distortion in a pathway of traveling wave. So ultrasonic wave also coming in different mode and shape. I have listed a few of them here. My interest is guided wave, bonded wave, surface bonded wave, or surface acoustic wave. Many interest in geophysics and geologists on this type of waves. They don't have that much application in mechanical engineering like a Lamb wave, which is restricted by a thickness frequency. Most of the scientists who solve these wave equations are geophysicists, geologists like Riley and Stornelli. They are coming in different shape also at the boundaries of the solid air, the Riley wave, at the boundary of the solid liquid, Schultz wave, stone lily as a boundary of solid, and different waveforms. They are mostly used again for geophysicists, and some they call them seismic wave as well, because they use them for the earthquake phenomena. This is our idealized illustration of interface wave propagating at the boundaries of the two-dimensional solid. And this diagram have the equation of motion and derived displacement. I built up a model. My approach was model-based development by numerical simulation. The solving the roots of stone wave has to do with the complex root of equations, wave equations, and it's evolved over time by advancing mathematical development and mathematical tools. One restriction is that there is a narrow range of existence for the stone wave. So I built up a model and extract the displacement and the time, which is the time of arrival or time of flight. So U1 and U3 are the components that I'm extracting. So what the model I built is doing is measuring the stress wave and then back calculate the strain, and the outcome is that this displacement component magnitude at the time the oscillation or the time they are recorded, and we can get good data from that. For example, one of the restrictions is that in aluminum and titanium, since the material property are very close, we don't see formation of the interest wave at the bond line of these two metals. But for aluminum and composite, since the difference in mechanical properties in order of magnitude, we can see the interface wave is forming at the bond line of these two media. There's a classic paper by Pillant, who created this region based on a ratio of the shear velocity and ratio of the density. We can see that if we have a stone wave or any other form of the wave. Anyhow, the wave moves faster in metals. It has to do with more attenuation in the composite, and in the next time into how we can use this data to do damage detection at the bond line of the hybrid bonded joints. So I used dynamic explicit solver for commercially known finite element code ABAC CAE. Isotropic section is aluminum, strapped to the anisotropic section of the composite. The bonding mechanism, and this table has a material I use for this simulation. Bonding mechanism is a chain of material and interfaces that you can see here, and the strength of the bond has to do with the weakest link in this bond. So regardless of the bond quality, I have constructed a pitch catch setup where I use transducer or actuator at one side and sensor or receiver on the other side, and several waveform creates in this configuration the Rayleigh wave anisotropic and anisotropic section. My interest in this interface wave at the bond line of these two sections, and I'm looking into that interface wave closely and extracting some data based on the damages that appears at the bond line of this structure, and I do baselining. For example, here the blue lines are undamaged when I have perfectly bonded, and these green signals are for when I have a crack at the edge of this bonded section, and I do baselining here. So that's the method. I guess before going to some example scenarios, that's a good place to show some examples side by side. So here in this top stack, there is a no damage, perfectly bonded joints. I have this bond, a notch here, and this is a delamination at the bond line of these two sections. And on the film animation below that, you can see again perfect bonded on top. There is an adhesive failure, which I have reduced stiffness, no viscoelastic property, which is, they call it kissing bond here. You can see the attenuation at the adhesive, and cohesive failure, exaggerated damage, crack at the edge. So those are all cases that I can extract the wave signal and do that for health monitoring or non-destructive inspection. Considering all the characteristics of the interface wave, we can use them for detection of several interfacial damages in bonded structure. Unlike many other type of inspection technique, the interface wave, they are not distracted by the thickness or the topography of the structure, because they just move on the surface and interface of the media. And so, for the crack and delamination, There are two types of damage: adhesive or cohesive failure. Delamination and crack, they're typical in hybrid bonded joints. The crack creates something like a bow wave, creates at the edge, and the wave propagate due to singularity here. You can see that. And delamination is a case when the bearing strength of the composite is lower than the strength of the bond. Sometimes we can see the crack is not happening, and the first or second ply of the composite get to fail due to out of plane loading. And that's the case for delamination. But anyhow, I created this model, and you can see some of the dimension and crack nucleation site here, or the delamination location. So if I have X and Y, I have crack propagation incrementally in X direction, and the location of the delamination is in Y direction. If the delamination is deep through the structure, then this interface wave is not very effective, because interface wave is only good for certain depth, and the amplitude of the wave decay exponentially through the thickness. So there are other methods like pulse echo, where we rely on the back wall effect. But anyhow, some of the results for this investigation, and you can see these charts, for this one and delamination. Like many other non-destructive inspection, again, the baseline here is the case that I have no crack or no delamination, which is perfectly bonded. Here, vertical axis is time in microsecond. Horizontal axis is the size of the despawn or delamination in millimeter. 0 stands for undamaged. For example, for the case that I don't have any damage, there is 34 microseconds for the wave to travel from transducer to sensor. Crack growth rate is 1/10 of an inch, and the increased slope is demonstrating the delay in time of flight. What it represents is that as the size or length of the despawn crack increases, the interface wave moves slower. And we can interpret that as a mode conversion of a Stoneley to Rayleigh wave, which is associated with single slowness profile. In delamination, it's not as linear, but the reason is that the wave is only good for certain depth to the structure, which is 1 and 1.5 wavelength of the incident wave. And beyond that, interface cannot detect any damage to the structure. Other damage is adhesive. Adhesive failure, it's at the bond line. It has to do, with the adhesive, the failure of the bond and one of the adherent, and also the degradation of the adhesive. Generally, bonding mechanism is a chain of material, and when I'm looking into the adhesive, failure is happening at the plastic range. So I'm looking at some parameters like density, viscosity, and the modulus of elasticity of the adhesive. So I have modeled the hybrid structure similar to the cohesive damage, but simulated the bond line with the viscoelastic media by expressive dynamic code. These two blue figures here illustrate, the phenomena that we hope to explore in order to characterize the state of the adhesive of the bond line. On top, you can see, there is a wave in pristine condition, which I can call it good bond, and there is no change in the mechanical property of the adhesive. And right below that, there is a wave, there is a adhesive reduced density, which you can see the attenuation of the wave. And there are some of the results, and as you can see, reduction in the density is leaning in higher wave velocity, which is in good agreement with the general wave equation, which is the square root of modulus of elasticity over the density. Another case for hybrid structure is a radius filler or noodles. Noodles or radius filler are composite structures which are used to filling the radius band of curved section, such as a skin stringer. As you can see here, in this quasi-triangular green shape here is a noodle, the skin stringer. It's not easy to inspect the noodles. There are some common damages in the noodle because we have to use a very small angle beam transducer or shoe, to inspect the noodles because of the accessibility. And there is some compensation factor for the curvature, which we are not. If we are not doing the calibration right, we don't get any good results. So my proposal was that to create a waveform at the right wavelength with respect to this radii to inspect the noodle boundaries thoroughly. And you can see some of the results here. all we want is that for the wave to diverge and converge at both ends of the noodle, something like this elapsed times that you can see here, and inspect the the curvature and the area thoroughly. There is a partial results, and like many other cases application, I have a pitch guide set up, a transducer and receiver on both sides of the noodle, very similar fashion. Displacement time history curve, show the results for some of the noodle crack assessment. And the rate of growth, again, is in tenth of an inch, that noodle crack from this side. And we can see here, the time of flight increases, that corresponds to the decrease in the wave velocity, which has to do with the disruption of the wave front, as well as mode conversion from Stonelli to Rayleigh wave at the location of the noodle. So time of flight assessment can be used for this damage detection as well. Last application is a roughness problem. By definition, roughness is a high frequency and short wavelength parameters of a finished surface, and like shown in this diagram on top here. Roughness is inherently a product of manufacturing process, and it's undesirable. In engineering, we might have some clearance issue or out of tolerance issue. For example, in composite, we have wrinkle or kink, and also roughness is a big issue as a fatigue life for all of the structure, including additive manufacturing. And fatigue is kind of surface phenomena. So in this work, we're looking into surface acoustic guided wave to characterize the roughness parameters such as width and height of these irregularities. And here I suggest a ratio for the by FEM representative. You can see the surface roughness pattern or lambda surface, which is a distance between successive peaks, and initial incident wave frequency and corresponding wavelength, which I call a lambda wave. So I'm looking into those parameters when I use a numerical study to investigate the guided wave propagation on the surface. Cutoff ratio is a ratio of the lambda surface over lambda wave. The physics for wave propagation behind that is, the Rayleigh wave attenuation increase with roughness. So ultimately, there is a cutoff ratio in which the wave do not propagate beyond that point, and you can see that ratio, for incident wave. In this figure, you can see this is again a simulation in time elapse of 2.5, 3.75, and 5 microseconds, and so forth. And if you compare the wave signal from right to left, you can see this is a smooth surface, this is a rough surface, and wave attenuation, partial attenuation, and total attenuation appears at this cutoff ratio. So again, this is a mostly very empirical study. With this method, we can measure the amplitude loss at a specific time, which known as decay. And also we can quantify the wave decay over time in a specific distance, which is attenuation. So lots of good empirical data can be extracted from this. And several good publication and invention disclosure patents came out of this work. And I leave with this summary page. I have to say thank you to many people who helped me in this project, especially Dr. Macmillan. Helped me in the past 2-3 years, to get into some of those interesting research ideas. And I'm looking forward for more collaboration. So looking forward to get your feedback, especially we are at the phase that we are doing model-based development, building a digital twin. So we have a semi-analytical fundamental analysis model, MATLAB code, and we have several test coupons bundled together at the lab to try to calibrate and do some experimental studies for verification and validation of this method. Thank you, and have a good rest of the day.